Okay, so good afternoon, and today I mentioned that we will have some explanation about the AI Cup. And today we are very glad to have the Professor Zhang from the National Zhongzhen University. And whether you know where it is in Taiwan? It's actually in Jiayi, so it is really far away from here. Yeah, so I'm actually very glad that for Professor Zhang and his favorite student Liang Yu would like to give a presentation for everyone. And to tell you the truth, this competition is actually have a very high maybe scholarship, right? And I saw there are more than 250 groups who join this competition. Yeah, so I believe the competition is very quite keen right now. Okay. Yeah, so I think maybe today we would like to maybe to understand, okay, what is the ORCID data set provided by this competition. Okay. Yeah, and what maybe today maybe the Professor Zhang would like to provide a notebook for us to train the model. Yeah, and I saw that the model is applied Resonate 50, and I think maybe we are able to maybe to find out maybe some algorithm and to make some comparisons to this algorithm. Okay. Yeah. So I think maybe today we'd like to spend 1.5 or even 2 hours each time and to give a presentation, and everyone is able to study that. Okay. And because Liang Yu already provided everything to me, and I shared it on the iClass. Okay, so maybe you could go log into the iClass and to see the results. Okay. All right. So maybe let's maybe have some. Let's welcome the Professor Zhang today. Okay. Thank you.
Thank you, Professor Chen. I'm very glad here today to introduce you the AI Cup. So this year the total award is up to $320,000. So I hope this award is high enough to attract you to join this competition. So today we have several parts of the short course today. The first part is to briefly introduce the contest, how to participate in this contest, how to, for example, download the dataset, use the dataset, and build a model. The second part is to briefly introduce the CNN model, because for image recognition or classification, CNN is a very popular model and very useful model. So I will introduce the concept of CNN. And then Liang Yu will introduce how to use Python and PyTorch. This is the deep learning framework. So you can use the sample code from PyTorch to build your own model. So let's start the lecture today. Okay, so the contest this year is about machine learning competition for ORCID recognition. So the competition description is Taiwan has a long history that we can produce high quality ORCID, but we know the property of ORCID, their flowers may look very similar, or their stems may be similar, but they belong to different categories. So how can we train different machine learning models to recognize a different species of ORCID? So because currently we don't have any software or tools that can help the farmers recognize the ORCID. Okay, so this is the website that you can reference for Chinese version or English version, how to participate in this contest. So this is the simple rule how to register or how you can join the competition. So the rule is very simple. Anyone over the age of 18, then you can join. Except if you are students, then you can earn the award and certificate, or maybe the pre-offer from the company. Okay, the registration is very simple. The team member can go to the website to register your teams, and I think just follow the steps of the website, then you can join the competition very easily. Okay, here I listed the award this year. We have the third place award, second place, and third place award. And then we have 4 excellent results award. Each one is $10,000. Besides for students, we also have the award for industry and student as well. So you have the chance to earn the first place also with the industry prize. This is for both student and industry. Okay, so the difference is this award is basically based on the ranking of your accuracy results. But for this part, different industry, they have their own interested species. So you need to have the highest accuracy from that particular species, then you can earn the industry award. But before announce the results, we don't know what species we need to focus. Okay. Besides for the industry award, we also have special prize for model efficiency to check. So if your model runs very fast and your result is above the threshold, then you can earn the model efficiency award. And we also have model novelty award. So even your results is not ranking in the first place, but you create a very novel model structure, then you have the chance to earn Model Innovation Award. Okay, so besides for the prize, we also provide the pre-offer for the students. So if your ranking is above the average, above the threshold, then you have the chance to have get the pre-offer from Trend Micro. So one advantage is once you get the pre-offer and then you really join the Trend Micro, then for the first months you will have $10,000 as your additional award. Okay, so I think we have a lot of award that you can maybe pay your attention to your model, for example, accuracy, model structure, or model efficiency. You can earn different awards. Okay, the competition rules is we have 2 phases in this competition. The first phase is to get the training set. Okay, so we have about 2 months that you can use the training set to build your model and test the validation accuracy. And then in phase 2, we will release public dataset and private dataset. So public dataset is you have like 8 hours to test the public testing dataset, and the results will be released on the billboard. So you can compare your results with other teams to see the ranking of your current results. But the results of private testing dataset, the results will not be released. So the final score will consider both scores as the final scores of each team. Okay, so this is the ratio, 30% for public dataset and 70% for private dataset. Okay, this is the schedule of the competition. So the competition already started from April 1st. So we have more than 2 months that you can download the training set to train your model. Okay, for the second stage, it's start from June 6th. So you can download 2 public testing dataset and private testing dataset on that day. And it open from 9 a.m. to 5 p.m. that you can upload your results for both testing dataset. Okay, the other schedule I listed here for your reference. We have the date you need to submit the report. Okay, so from my competition experience, we need students to provide the report to describe the model structure or how novel their model is, how to execute their codes. So we are able to verify that your code is valid. Okay, so this is the schedule that we will announce the final list and have the award ceremony. Okay, so we provide the Chinese version and English version from the competition website. So if you need more details, then you can go to the website. Okay, that is the brief introduction of this contest. Any questions so far? Okay. Next, I will briefly introduce convolutional neural network because today we will provide a simple code of CNN models for you that you can base on this code to develop your own model. So let's see what is convolutional neural network. Okay, before we introduce convolutional network, I want to introduce image convolution first. This is a very important approach for image processing. So why we need image convolution? So basically, if you want to create some effects of the images, for example, you want the image to be clear or have more details, or you want to provoke a certain mood or alter the color and shading that can affect aesthetic of the images. So that's the goal of image convolution. This is the example when we apply image convolution to images. For example, you have the original image, and you have, this is what we call mask or filter. Then you can apply the filter to the images to have different effects of the image. In this case, it's image blurring. So after apply the image convolution, the image becomes blurred. So we have other image effects, for example, sharpening, or edge detection, or relief. So if you're familiar with Photoshop, it provides maybe 10 or 20 several different effects you can use for image processing. Basically, we need a spatial kernel. This kernel usually used for 3x3, 5x5, or 7x7. And the value in this filter is defined by the expert. So if we use the filter like this, in the center we have 1, then besides we have -1 here. You apply this filter to the image, then you can get age-enhanced image results. So first, let's see how convolution is performed. Okay, so here the example, we have 6x6 original images, and we have 3x3 filters. When we apply the filters to the images, okay, the operation like this. Basically, we need to like flip the filter horizontally and vertically, and then it just like put the 3x3 filter on this position. So you have 9 value here. You have 9 value in these images, and then we just calculate the results element-wise. Multiplication and add the results of all 9 positions. In this case, here is 1, right? So on the left top corner, it's also 1. So 1 multiply 1, 0 multiply -1, 0 multiply -1, and 0 multiply -1. Okay, you just multiply the corresponding position and get the results and summation them all together. You will get 3, right? because we have 111 here. So we have 111 in the diagonal of the 3 by 3. Okay, so the summation is 3. And then we have the results of first position. Next, we will move the sliding window to the right, so we can calculate the results of the 9 values. And the summation is -1. So we can continuously moving this window from left to right, from top to bottom, and then eventually we will get 4 by 4 results. Okay, this image is just related. Oh, okay.
Excuse me, I have a question. It's a nice presentation. Thank you for this. You mentioned that we flip horizontally and vertically the kernel.
Yeah.
Otherwise, we make a transpose of this matrix.
Yeah.
This is the definition of convolution.
Yeah, that's
However,
right.
This is not observed in code. The kernel is not flipped. It is put as is. It is not flipped. I mean, this operation does not seem to be in code.
You mean?
I mean, what we do actually in code is correlation. We just take this kernel and just apply it. I mean, we flatten it and make a dot product between these vectors. But we do not flip the kernel, this filter.
Okay.
As far as I know, I just want to like ask you.
Okay.
Where did you get that? I mean, the flipping of the kernel, this operation of flipping the kernel before making this dot product.
Okay. So normally, when we apply convolutions from the kernel to the images, we will flip the kernel first. So in this case, this kernel is the results after flipping. So we can like transpose, just like you said, transpose this matrix, then have vertical and horizontally flipping results. And then the operation is based on 2-dimensional. So you can use like 2 for loops to calculate the results. How these corresponding 9 positions, you can multiply the results and add to get the sum. Okay. Okay, here we can see the results. The filter, we have 3, 1 in the diagonal. So in the results, we can see we have 3 in the diagonal. This pattern is a very special pattern we want to find. So here we have 2 cases of 3, 1 in the diagonal. And then the corresponding results, we have the highest value in these positions. So which means from this results, image after convolutions, we can actually find the spatial pattern we want to search. Okay, so this is how we perform convolution. One thing you can notice is if we apply 3 by 3 filter to 6 by 6 images, then we will have 4 by 4 results. You can relate these results to the previous slides. This is just the original image. This is the image after convolution, and this is the 3 by 3 kernels. Okay, so why we need a convolution originally from image processing? Because just like you have already seen, we can like apply different effects. For example, edge detection or image enhancement. Then, if we can apply different filters to the images, then we will have a lot of different image representation. This representation can be considered as the image features. So this is the case when we do face recognition. So once we have the original images, we can apply different filters to the original images. So you can have a lot of different convolution results. So these results can be related to, for example, low-level images. Just see the direction of the edges. And then you can apply filters again to these images to have another image representation. For example, mid-level feature representation or high-level feature representation. So the convolutional neural network gives it a lot of chance to have a lot of different image representation, or we can call that image features. So basically, the model will select or learn what feature is best for the goal. If we want to recognize face recognition, or in this context, orchid recognition, what is the best image features for the goal? Okay, the CNN can automatically learn the filter because from the previous slides, you already see the filters is designed by the expert in image processing. But for CNN models, it learns the kernels automatically. Okay, so we can see another cases when we need to do car classification, elephant classification, or chair classification. It can learn different image features automatically by CNN. Okay, this is another reason we need a CNN model. This is the example of beak detector. Actually, we are interested in the beak of the bird. Okay, so one thing you can notice, the beak just occupy a small part of the whole image. Okay, we are only interested in this small region. So when we apply image convolution, it's just like the sliding window. You can slide over the whole images to find the region of interest. Okay, another reason is the region of interest may appear in different places in these images. Sometimes in these images, the beak is here. For these images, it's located in the center. So once we have image convolution, it can sliding over the whole images. And then even this region is located in different images. It's okay, because we already slide over every picture, every position to find the region. Okay, so we already know why we need the convolutional operation. And here is how to combine the convolution operation in the CNN model. So if we have the input for the CNN model, then in CNN models, we call that convolutional layer. Basically, in this layer, we will have a number of different filters. For example, 50 or 100. So when you design your CNN models, you can see we actually apply a lot of different filters here to extract the feature representation. Okay, so after we apply convolution to the images, the convoluted results, sometimes we call that feature map. So this is what we call feature representation as well. Okay, you will have a lot of feature maps that can help you for image classification or other goal in your model. So in this case, if you have two filters, you will have two feature maps. From the previous example, if you have 100 filters, then you will have 100 corresponding feature maps. Okay, except for convolution layer, we also have another layer which is called max pooling in CNN. Okay, so let's see how max pooling is operated first. So basically, max pooling is operated by a local region, for example, 2x2. So in these 2x2 regions, we find the maximum number here. So in the first case, the maximum number is 3. Okay, in the second region, the maximum number is 0. Okay, so you can find the maximum number in these 2x2 local regions. So here, originally we have 4x4 feature map. So after max pooling, the feature map will become 2x2. Okay, the reason we need max pooling is it's just like the operation of subsampling in image processing. this is the subsampling results. If we just shrink the original image just half in the width and height, then you can see after subsampling, the image is still very similar to the original image. Even the details does not change significantly. Okay, so one reason we apply max pooling is to reduce the size of the image. Because if we can reduce the size, then the model parameters will also become smaller. Okay, if you continuously use very high resolution images in your CNN pipelines, then you will have a lot of model parameters. So, the reason to apply max pooling is to resize, make the size of the image smaller, and keep the content. And on the other hand, we can reduce the model parameter as well. Okay, so basically CNN is just contain two operations, convolutional layers and max pooling layers. So in this case, originally we have 6 by 6 images. After convolution, we have two 4 by 4 feature maps. After max pooling, then we will have two 2 by 2 feature maps. Okay, so this is how CNN operated in this simple case. Okay, so before we introduce the recent new CNN models, you can see the concept of CNN just apply convolution and max pooling alternatively in this model. So in the last step, we will produce a lot of image features, or we can call feature maps. So the last step is to flatten these feature maps. And then the 1D image features can use as the input to the fully connected neural network. Okay, the flatten operation is also easy. From the previous steps, we have two 2 by 2 image maps, feature maps. So we can transform this 2 by 2 by 4 by 1, 1D vector. And then we concat these two feature maps together. Then we will have 8 by 1, a 1D feature vector. So once our 2D images can transform to 1D feature representation, then usually in the CNN models, we have several layers of fully connected layers. These layers is used as the classifier. So in CNN models, you can see it contains two parts. The first part is to extract image features. The second part is to learn the classifier together. Okay, and then the model will output the results. The classification results for class 1, class 2, class 3, the probability from each class. Okay, next I will introduce some CNN models that has been used a lot in the past year. The first CNN model is LANET 5. Okay, so we already know CNN models, convolutional layer and max pooling layers. So in this model, we can see the structure is very simple. This is the original images. Then we have the first layer, which is convolutional layer. We call that C1. And subsampling layer, max pooling. And we apply convolution, max pooling again. Then in the last part, we have two fully connected layers. The dimension is 120 and 85. And output is 10 dimension, which refers to the digit recognition problem. We want to know the input image is 0, 1, 2, 3, 4 to 9, totally 10 class. Okay, so we will output the probabilities for each classes. Okay, after LANET 5, we have VGGNet and AliceNet. So basically, you can see the design of AliceNet and VGGNet just use different number of convolution or max pooling layers. In this case, AliceNet, we have two convolution layers, followed by 1 max pooling layers, and 1 convolution layers, 1 pooling layers, 2 fully connected layers, and the last one is softmax layers. For VGGNet, we have a deeper structure of the CNN model using more layers of convolution and max pooling layer. So maybe you will wonder why this model looks like this, why they designed the model like this. So theoretically, we don't know why, but the experimental results verify this model works better than the previous conventional model. Okay, next one is GoogleNet. You can see GoogleNet is a very large and very deep structure of CNN. But the design of GoogleNet, they have their own theory because the model is composed based on inception module. Okay, so we can see the inception module like this. We have 4 parallel paths of the module. It is from 1 by 1 convolution, 1 by 1 followed by 3 by 3 convolution, or 1 by 1 followed by 5 by 5 convolution. So this just like we don't know what kind of convolutional kernel we need to use. 3 by 3, 1 by 1, or 5 by 5, we don't know. So we try to combine different convolutional filters. Maybe it can give a variety of feature representations. And then we will concatenate all feature representations together in the next step. So you can see in GoogleNet, the inception module just use 1, 2, 3, 4, 5, 6, 7, 8, 9. It used 9 times in this GoogleNet. So even this is a very large, very deep CNN models, the design is not arbitrary. Okay, it's based on the inception module. Okay, let's see the revolution of CNN models. Okay, from the earlier machine learning models, such as, for example, support vector machine we use for image classification, we can see for the dataset ImageNet, the classification error is reduced year by year using different CNN model, AlexNet, VGG, GoogleNet, or ResNet recently. So you can see the top 5 error is decreased gradually. And the depth of the model is increased gradually from 8 layers, 22 layers to more than 100 years. So ResNet is a model that can build a very, very deep CNN models. So we can see the layer of ResNet model from 34 to 152. You can see the layer is getting deeper and deeper. But the time complexity is not larger than VGG because this is some details. Maybe you can just know the concept because the ResNet we don't have fully connected layer in the end. So we reduce a lot of model parameters in this model. Okay, the last thing is maybe we can visualize the feature map or learned kernel because we already mentioned that CNN can learn the filter automatically that is suitable for the goal, for example, image classification. So how this learned kernel looks like, what the image features look like. Okay, this is the example of bird recognition. So we can see the results from VGG 16 models. This is the first block of features we can recognize. So basically, the image features just like the original bird very much. Okay, but for the second block of the feature map, we can see the image feature just concentrate on the shape of the bird. Okay, so in a lot of feature maps, we can see it only concentrated on the shape of the bird. For the block 3, we can see it just transformed the shape of the bird and further concentrate on some like a key point of the bird. For example, a key point from head, key point from tail, and key point from the wings. Okay, so for block 4, we only have just few key point or very important small regions left in this feature map. Based on the combination of these feature maps, then we are able to recognize what bird it is. Okay, in the last part of VG model, we can see it further generalizes this key point to make it larger regions. So you can consider maybe this as the Gaussian distribution model. Maybe the center is the most important point. And from every directions spreading for other directions, then the importance becomes less. Okay, so this features just like the generalization of the key point. Okay, this is the filters it learns. So we can see this is the filters from the first 6 layers of the filters. So the filters is 3 by 3. Actually, we cannot like read or get the meaning why the filter like this. Okay, so this tells us maybe you can further analyze the image features because it may tells you how the model learns how to recognize the birds. But it's not meaningful to see the filters because it tells us very less why the filters like this. Okay, we will have many applications that can solved by CNN. For example, AlphaGo. Okay, this is very famous like 3 or 4 years ago because the AI defeat the world's best chaser. Okay, so even this is for Go game, but if we can apply CNN for this goal because we can consider the current chessboard as the images, and we can formulate this problem how to choose the next position as the classification results. So if this is a 19 by 19 matrix, then we will have 19 by 19 positions. Which positions has the highest probability that is the next move? Okay, so you can see this is the very classic problem. Use image as input and output the probability of classes. So this is AlphaGo. Okay. Next application is speech recognition. The speech data is 1D data, but we can calculate the speech data to calculate its spectrogram. Okay, so it just reflects the time versus frequency. Okay, we can calculate at one moment and the magnitude of every frequency component. Then it can become the 2D matrix or a graph. Okay, once we have the images that transform from the speech data, then we can apply CNN. Okay, next one is text classification. Okay, for example, I want to recognize this text, I love my new iPhone. Okay, basically we can transform the character or the word into the representation using word embedding. So every word we can find its representation of 1D vectors. So I love my new iPhone, we can have like 6 columns by placing their word embedding 1D vector altogether as a 2D matrix. Once we have the 2D matrix, we can consider it as the images and use linear model for classification. Okay, So you can see we can apply CNN model to a lot of different problems. Once you can transform your input data into a 2D matrix, then you can use CNN. Okay?
What do you mean by text classification?
Text classification is
Is it topic of text or?
Topic is one example. For example, it's the topic about sports or the politics and so on. Okay. So this is the end of the introduction of CNN. Okay, any questions?
You mentioned shallow networks before when you compared them. How many layers do you consider shallow?
Usually it's just one layer because from, for example, support vector machine, decision tree, and other machine learning models, usually we need expert to help us find the imagery representation or features. So once you have the features, it's just one layer, and use this one layer directly into the model. So we call that shallow version.
Sometimes different people count in different ways. Do you count like input is 1 and output is 2? Or like maybe you do not consider input, so just one output, right? So this is shallow. If there is one hidden inside, there would be 3 layers.
Yeah, that's right.
A hidden output, so that would be not shallow.
That's relatively shallow because we are referring deep learning because usually we use multiple layers. If your deep learning model just have 2 or 3 layers, so it's relatively shallow.
Okay, so 2 hidden layers. 2 hidden layers, 4 altogether would be considered deeper, like not shallow?
It belongs to the deep learning model, but it's not that deep.
Okay.
Okay.
When we go back to Lenet 5, for example, and we have 2 convolutions in sequence, what's the depth of the kernel? I mean, not in specific Lenet 5, but I mean, there is a good picture in Lenet 5. So I mean, if we go to C3 kernels, what would be the depth of the kernel?
Okay.
We know that it's width, height of the kernel.
Okay.
Is it depth?
Okay. The depth in this case is 6. Okay, we have 6 different. We have 6 different kernels, so we will have 6 different feature maps. So in this case, the number of kernels or the depth is not that high because this version is like years ago. But in recent CNN models, the number is very large.
When we consider kernel, we have how many dimensions do we have in the kernel?
Usually we use 3 by 3, but 5 by 5, 6 by 7 is also available.
Dimensions like width, like number of rows, number of columns, and number of depth.
Yeah.
In the kernel.
Yeah. So for example, 3 by 3 by 100.
Yeah. So that 100 comes from the previous feature maps.
No. The number of feature map, for example, in C2 and C3, the number is independent. You can design 100 here and 50 here. So it's not related. So because once we have the 100 images here, then you can apply another 50 filters to these images.
Also, you mentioned that CNN performed better on AlphaGo. How much better and why? Than fully connected layers. You mentioned that CNN performed better on AlphaGo. And how much better? Is there any information on how well does CNN perform on this specific task, AlphaGo?
I don't get your question.
他说那个例子是说 CNN 比 fully connected 好，那说这是什么根据？就是从哪里的 reference 可以知道说 CNN 在 AlphaGo 的例子上跑比 fully connected 那个 layer？
I didn't say that. I didn't say CNN performs better than deep learning in the application of AlphaGo. I just mentioned CNN is applied for the very different questions AlphaGo because it's just the Go
Can
game.
we go to AlphaGo slide?
Okay.
就像前面下面
Yes, but CNN performs much better.
Okay. Fully connected layer can be okay, but CNN performs much better because CNN just use the image as the input, but fully connected layer just use 1D input data. For example,
Flatten, you mean?
Yeah, flatten.
This grid, like we have grid of all of these what points or whatever, we have that
Yeah.
black and white, and we just flatten in fully connected layer, but in convolution we just keep it.
It's not only the reason just flatten to 1D because when we use fully connected layers, we can also extract features from 1D image data. You can transform 2D image to 1D, right? So you can also use 1D images as the input to the multiple fully connected layers to extract features. But CNN performs better than fully connected layer because it uses the concept of filters. Filters just find the properties of local regions of the images and build us the image features. Fully connected layers just consider the global information because it's fully connected. So it's just like, does not like the filters concentrate on the local properties of the images. So if your input is images, it's better use CNN than fully connected layer of deep learning model.
So the output is next move. The output of this problem, like from this model, is the next move that we should do, right? To think again.
Yeah. But for AlphaGo models, actually, it has another model co-work with CNN. We call that a value evaluation model. Okay, it assesses if you decide to move from CNN, then it will give the score, maybe to assess the score is high enough. So basically, AlphaGo has two models co-work together.
And another question is about build feature maps on the bird example. You presented these bird examples, and it's kind of interesting to see it because I used to see the feature maps which are starting from during ASIC, like edges or corners.
Mm-hmm.
But here we see in the first feature maps the whole picture of the bird, which is different.
Mm-hmm.
And the feature maps, I think they should be of different size because the kernels are different, like 1 by 1, 3 by 3, or 5 by 5. And so, did you like precise everything, right? So we see.
Yes. Here the results are just after resizing, but for some CNN models, it can maintain the output size for each convolutional layer. So if you see more CNN models, you will see model like this. In this case, the feature map, the size is different, but we just use the same size for visualization.
Okay, thank you.
Okay.
You can scan the QR code generated by the browser and just click on this link and you have access to the whole folders on the Google Drives. Okay. So in case there's someone that's not familiar with the Python, so we'll just quickly go through the Python introduction. So this is for the environment setting and the installation of the Python. So in this example, we will use Colab Notebook as the platform to execute our Python programs. So the Colab Notebook does not require installation on your local host, the PC, and even notebooks
can just access it on the browsers. And another way to execute the Python program, you can use Anaconda or even use the Python that installed on the CMD in your window, or even use Brew Home or on the Mac OS. So this is about the virtual environment of Python. So the pros of the virtual environment, it allows you to create multiple individual virtual environments to prevent the conflicts of the package. And one of three famous virtual environment management tool might be Conda, virtual environment, vEnvironment, and pip virtual environment. So you can go on Google and search how to create a virtual environment, or even use Anaconda prompt to do the Conda execution. So these are lists of the cross-platform software. So the IDE might include Visual Studio, which also known as VS Code, PyCharm, and Spider, Jupyter Notebooks. And also you can just use Terminal Plus editors, like you use Sublime as the editor and then use the CMD as the terminal, and you like the same as the Atom and VS Code. So here we will use Colab, and we won't use this because Colab provides us the GPU and also the online executions for Python. So the special of Python is it does not require to first declare the variable type. Like you don't need to declare that the variable become int, float, or double, and use built-in functions to transform the type of the variables between each. Like you can transfer from string to int or int to string. So this is an example. Like A, you declare it as 1, 2, 3, 4, 5, 6, and then you can use as the str here, and then make it becomes a string of 1, 2, 3, 4, 5, 6. And this is int, float, bool, like true or false, list, tuple, dictionary, string, and none. So like here, the example of A may be 100, and then use a float to convert it to float, and you can check the type of this object. And this is the string, and also you can use a bracket like this to convert the A into the string, and then use the int and take it as base 2. Wait, let me check. Okay. So here, 100 in the binary system might be the 4, and if you change this as 8, then it will be 64. Then here, you can also change the string, like 100 to the list, become like this. And this is another example. You can use zip to combine two lists together to become a dictionary. So this is like when you're printing, you can use the brackets and then use the .2f to indicate that for this variable ACC, you only want it to be 2 floating point, 2-digit floating point. So it will become like this. And also the operator. This might be the exponential. XOR. 这跟我想的是一样的吗？ Okay, so I'm not quite sure this line, but from here you can see that the float will be, the 1 will become float and the 1.5 will become int will be 1. And also in here, you can use, like in the default math, you can use mode, the built-in function we have mode. And also in the math, which is another library, you can use the math f mode, which is the mode for the floating numbers. And this is the list and tuple. So the list, you can change the value in the list, but the tuple, you cannot change the value in the tuple. You can access it, but you cannot change it. You can modify the number in the tuple, the object in the tuple. So this is another indexing and slicing. So this is like start, end, and steps. So you can use this in the range or enumerators, and also you can use in a list, like just taking the first 10, or you just taking the last 10 object in the list. I mean item in the list, and a dictionary. So we have the update. This is a dictionary when you declare the dictionary object, and then you use update to change the update's value. Item to get this the item in the dictionary, and the keys and values. So here 2, A 0, and then B2, like this. And this is a string. So they include a change line, tab, and then bit. And you can use joint to combine the object in the item in the list together with the dash. And a boolean, just very convenient for you to check the stage, like it executed or not. And if else and else. If and else. So for loop, we use this in the machine learning to check to iterating through the batches and the epoch. And you can use the path to just skip one of the iterations. And you can use range or even enumerator. Enumerate is faster than range, but I think in Python 3 they combine, like in Python 2 we have X range, and in Python 3 it combines range and X range together to make it faster. But usually we use enumerate for to go through the whole iterations. So this is the ways when you open the file. Like in this competition, we have the label.csv. Then you can use with open, then the file name, and then read, and then also the encoding UTF-8 to read the file, and then do the following operation to this file. And functions, we'll see later. And built-in function. This is just the built-in function that Python have. Okay, so we're done with Python. Then we go through the PyTorch tutorial. For this one, it's much more important in our sample code, because it will relate to our sample code. So this is the presentation that made by our PhD students. Then the introduction. So what is Python? PyTorch. PyTorch is an open source framework that for the Python data scientists to do the machine learning. So its feature is it has the GPU accelerations, and also automatic differentiations and dynamic computation graph. So this one is different than the TensorFlow. So it will, like, when you execute to the list line, then it will generate the whatever you call a last line. But in TensorFlow, it's static computation graph. So you need to go through the whole. You can go through the whole program. Then you will not, like, you start at this line and then get a result at this line. So this is the percentage that the PyTorch papers, or let's compare to the TensorFlow papers. So you can see at 2017, the PyTorch might not be very common framework on the paper, like you see in the conference paper. But till now, like 2022, it's almost like above 75% compared to the TensorFlow. So like more conference paper, like GitHub paper with code, already use PyTorch instead of TensorFlow. And this is the installations. So at here you can select like whether you want to install the PyTorch on the Linux or even the Mac OS or Windows. And you can like just by clicking the box, then you can just they will generate the commands, and you just copy this command and execute it in a shell. So at here we choose the stable. We usually choose stable, and then Linux. If you use Ubuntu, then you use Linux, and pip, Python, and Conda 11, or even you use 10. I think 10 already support the RTX 3090, and then you just copy this code and then execute in the shell. Then you add the installer dependency for the PyTorch. And this is for the NVIDIA GPU driver. So if you want to check the driver's condition, you need to also want to use the NVIDIA GPU. You have to install the drivers. And the installation path will be under this on the Linux, or even this under the Windows. So the tensor and mechanics. So tensor is the multi-dimensional dimension arrays, and the shapes will be the number of elements in each dimensions. So for example, if we have the instance that have 10 badges, and of the 255 times 255 RGB images, the shapes of the instance will be 10 to 3 to 256 to 256. So which indicates that this is a 10 batch and then 3 channels, and then the height and weight will be 2x6 and 2x6. So also note that the PyTorch is the channel first for its tensor format. So the shape of the image will be the batches and the channel height and weight format. Like if you're using OpenCV, it will be HWC. So the tensor creations. So this is a constructor when you create the tensors. So like this, you use 1 to 1, 1 to -1, and 1 -1, and you will generate the tensor of the instance of this tensor, these values. And also you can just create it from the NumPy array, or even you can transfer it from the NumPy array. So this example is like you initialize the NumPy array, and then you use torch tensor to make it like become the PyTorch tensor. And also you can use D type to indicate its its type, and the device to indicate this tensor will be put on the CUDA 0, 1, 2, 3, 4 or else, or even CPU. So for these functions, we have two functions like toTensor. This is a function and a toTensor class. You can use either one to transfer your NumPy array or array to the tensors. And to be noted that we have to normalize because the RGB range is from 0 to 255. We need to normalize its value from 0 to 255 to 0 to 1 to fit the flow tensor to help us to easier to compute it on the GPU. So this is an example. Like we have an image, and also the PyTorch use the PIL, the pillow, as its default way to load the image. So you can use if you load the image with PIL, then you can just convert it to the tensor. But if you use like OpenCV, you have to maybe change the image format to make it fit the PyTorch image format. So this is an example. You can use torch once to initiate the 4 times 4 is 1. Then you use the slicing index to make this column become 0. And this here demonstrate the in-place operations. Like you can use, like normally when we use the asterisk mark, it will mean the modifications. But if X and identity, this two is the PyTorch tensor object, it would just apply the element-wise modifications instead of the normal modifications. And this one you have to assign a value to assign a variable to store the result of this modifications. But if you use like this is another way, like add. If you use add 1, like this is x and 1 1 1 1. If you use add 1, it will give tensor 2, but it won't change the x itself. But if you use the dash after underscore under the add, it will change the x itself. How to say this? If anyone doesn't understand what I said at here, because it might not be very clear to elaborate this one. So if you're using add this operation, these functions, it will automatically add this add the x0 by 1. But when you check the x again, you can see that here the x does not increase by 1. Instead, if you use the add and then underscore after it, it will automatically change the value here. So this is the difference. So the broadcasting. So we know that if the matrix multiplied by a matrix, the dimension should be matched to do the operations. But if you're using, like, you can consider broadcasting that you don't have to resizing the matrix one by one and each by each. When you use broadcasting to like here we have the 1-to-1 tensor and the value of it is 5, and we have here 3 by 3 tensor, 3 by 3 matrix, and the value is 1. So by this broadcasting, this 1 times 1 tensor will be extended to 3 by 3 to fit its modifications purpose. So these are the two rules that the tensor are broadcastable. So each tensor has at least 1 dimension. So if a dimension like here is 0 in here, like you don't even declare or initiate any value in the tensor, then the size will be 0. It's not broadcastable. But if the tensor is have at least 1 dimension, and also the starting at a trail, which means the last 1 dimension, it must either or be equal, and one of them is 1, then it is broadcastable. Like here is 1, so it's broadcastable to the 3. So it will automatically extend from 1 to 3. So here is the autograph mechanism. So the autograph is one of the features that the PyTorch have. So like for this, y equals to wx plus b, and we have the x variable and then w variable. Then we know it has the operations which is modified together, and we have another operations that this result add with the b. And in the PyTorch framework, we won't immediately to calculate the result of x, w, and then b. We will just have the temporary state to hold is to wait for the backpropagation to get its derivative to update the neurons. So at here we have the y dot backwards. The y should be the lost that the predicted label with the true labels. So it will give you some values, and when you call it backwards, the backpropagation will update the value depends on what you get for your lost. So here, when you backpropagate that, you will do the partial derivative to b and to w to calculate the values that it have to the gradients for the value, and later we'll use the optimizer to determine how to schedule how to make the value change by its derivative or its gradients. So here is the one of the if you set for this one, you have to set the required grades to be true to compute the gradients. If the required grade is false, then you cannot compute gradient, and you will report the errors. So here also have another context manager like torch.enable grades, no grades, and set grade enable bool. So if true, then it's equals to true, and false equal to false. And this is enable is true, no grade is false, like this. So for this example, we see that the required grade is true, and false. But if x involved with the operation that x involved multiplied by the w is here the required grade is true and here is false, then the x here will become true because it has the modification with the variable that its required grade is true. And here, so here is like when you use with torch with no grade, the number here will not do the number the variable here is required grade will become false, so it won't compute the gradients if you code the backward. And here is the decorator to have the same ways to set its grade enable become true or false to make it differentiable or not differentiable. So also we have to move the data to GPU or even in CPU. Like if your model already put on GPU, but your data is just on the CPU, then it cannot the GPU cannot compute those data because those data are in the CPU instead of GPU. So you have to use to CUDA or to put your data to a GPU so the GPU can compute those data. So here is the way to use .CUDA to put your tensor to a GPU or to and indicate the devices to put your data in different numbers of GPUs. And also you can use the .CPU function to move the data from GPU to CPU if you want to do some visualizations. So if you didn't define that what CUDA, what GPU, so if this is one data, and this is the CUDA, the default, you will give the default CUDA object, and how to say it? So here we have CUDA 0, CUDA 2, and CUDA. So here we clearly indicate that if we have 3 GPUs, then the index will be 0, 1, 2. So here the CUDA 0 means the index 0 GPU, then CUDA 2 refers to the index 2 GPU. So if you use you initiate CUDA 2, then when you call here device equal to CUDA 2, you will make your X object, the torch tensor, from the CPU to the here is 0, so move it to the number 0 GPU. And here, if you just use the CUDA at the end and without declaring that which device the data will be put in, then it will default to the first GPU. So here will be the 0. And this is some symmetrics. So you can use with torch device. Then mostly the data, the variables involved in this in here will be moved to GPU 1. But you can also just declare it that move to GPU 2 or etc. So then here is the data loading and processing. So we will use these 3 classes which PyTorch provided, and also the torch vision that PyTorch provided. So here we use dataset, data loader, and transforms. So the dataset class, abstract class, have 2 methods. One is map style dataset, one is iterable style dataset, and the sample code we use in the Colab will be the first one, the map style dataset. Then here is an example. We can inherit it from the dataset that we declare here, what we import here, and then we modify it because we have the default class. Then we just use the default class and then modify some of the variables here. So we have self image label, which might be the files that we read from the Windows by using the pandas, and also we just declare the image path, image directories, and also some transformations that pass to the dataset, and also a target transform. And here we will return the image label, the length of the image label. Like if we have 10 different classes, then here will be returning 10. So here is the way if you want to self-defining the get items or length by yourself, or else you can just use the default dataset object class. And here is the data loader. I'm promoting that using distributed data loader, but if you just using one GPU, then you can use data loader. But if you have like 3 or 10 GPUs, you can use distributed data loader. Distributed data parallel, I guess. And here we have the data set, which is what we define here. And also the batch size indicate like how much instance will be sent into the models for one batch. And here we have shuffle, means that the data set will be shuffled or not. And sampler, if you use the distributed data parallel, then we have the sampler to decide which batch goes to the GPU 1, 2, 3, 4 or else. But here we're using the data loader, so just using none. And number worker, like you can use 8 or 16 or else, like depending on how many core your server have. Like if your server have 20 CPUs, you can use 10 or 20 for the number of workers. Okay. So here's the torch vision is about the data transformations. So mostly we do the data transform is for the data augmentation and normalization, and also we have another, mostly for these two, and we have another functions that can help us to do a series of the transformations to the image. So like here we define augmentations, and we have a series of transformation like the random crop 224 to 224, and then have color jitter, which is change the image brightness or darkness, and grayscale, and also have the Gaussian blur, horizontal flip, and also after this series of transformation, we change it to tensors, to the tensor. Then we feed those tensor into the models. And this normalize depends on how like this object I do have it normalized in my sample code, but here did not indicate what normalized is it, but usually we have normalized at the end if you do calculate the standard variance and means of the dataset. So this is an example if like the self-defined VGG module. So it inherited from the Torch module. And then here is the operations that when the tensor fit into the models, the behavior of the tensor will be. So here we have its features and average pooling and then classifier. The classifier includes a series of layers. Like here we have the first layer like linears. Like the dimension will be like this, and then we have a ReLU behind after it, and then drop out, and then do it linear again, and then ReLU drop out linear. You can have many stacks, many blocks of the classifier. So here is the place you define a series of the series of actions that you want your tensor may have when you pass into the model. And here the forwards will be the actual flow for a tensor goes through the model. So here the x will be the tensor that feed in the model. It will pass the features here and then get the features and then pass to the average pooling and then do the flatten and lastly do the classifier. And then you will get the return value after for completing these actions. So here is the loss function we will have. So loss function here we have two different ways to initiate the loss function. One is from the class and one is by the functions. And here we usually use the cross entropy loss to define to get a loss for the classifications. So here is the optimizer. Okay, optimizer. So here we import the torch.optim as optim. Just you can even not using this, just import this, and then you will use the one of the optimizer that under the optimizer, the stochastic gradient descent, and you will just put all the parameters that model have into it, and it will compute. You will get the values. You will compute the gradient by the value that you get from the loss, like the true label and the predict label, and you will use the optimizer.step to actually update those parameters. If you didn't call this, then the parameters in the model will not be updated. And here also we have another. It's called scheduler. You can initiate instance of scheduler or not. It depends on what your tests require. And here is the training and testing. So here is the trait of the models. So if you use model.train, it enables the model to become the training mode. And if you use the model.eval, EVAL, and then the bracket, then you will move your model from the training mode to the evaluation mode. So the benefit from it is you can become faster if you change to evaluation mode because it does not require to compute the gradients. So this is the training pipeline in the loop, and you will see later in the sample code. So you will fetch a batch of training data from data loader, which we retrieve an instance, a batch from the data loader. Then we, in the loop, we will compute its forward, and then also compute by backward to get its value, and then also updating the parameter in the models. And here we will, what we retrieve here will help us to do the gradient computations, which the optimizer will do. Okay. So lastly, the serializations. So this is when you want to save your model, you want to load a model which others provide you. Usually in PyTorch, we will save the model with the pico, so which is a serialized method to serialize the parameters in the models into the smaller size of object. So here we have torch.save and torch.load, which is like when you save torch.save and then the object here will help you to save to serialize the models by the Python Pico library, and also load, which is load the serialized object which by the Pico and then load it to the memories. So usually the file name here will end with .pt or .pth. So you can use torch.save model static here, and the path will be the path that you want this model to save, and also load. Before loading, you have to create an instance. If you want to load a resonate model, then here you need to have initiate a resonate model here. So when you load this model, the parameter in the model you load will replace with the previous initialized one. Okay, so questions? If no, then we'll go through the simple code. So do everyone have the simple code run already? Okay.
Could you introduce the interface first?
Okay. So
the function of this button.
Okay. So this is the Python Colab. Then for each cell in here, we can for each lines in here, we say it as a cell. Then you can just press the run button. Then it will execute this line in this cell. So here I use the exclamation mark to install the exclamation mark and pip install the NumPy library package. Then here is the lines that if you want to connect your Colab with the Google Drive, then when you click this, you automatically if you click on this icon, it will automatically create this cell. And then when you execute it, it will jump. You have a pop-up windows to ask you to authorize the Colab to have access to your Google Drive. So here I already executed. So you will say that mount to the content drive path. So here, because if you executing these lines, the difference would be here I create a folder. This is my Colab notebooks directory, and here I have the folder tutorial and the folder AI Cup. So if you click on the files and then create another instance, like save the instance in the Google Drive, then the instance will be created in here, the same folder under the Colab notebooks. So the difference here is you have to change this one to either you just create another folder and name it, or you just delete it to run it. But here I use AI. Here my folder is AI Cup, so I just execute it. And here we use a percentage, meaning that we will change the whole environment a path. So the path will be changed to here. If we use the exclamation mark, it won't change the path, the environment path to this directory. And here the matplot here is used, the inline is just later if you want to use the matplot library, you don't have to use plt.show to show the image in the shell. So in the folder, you can see that we have two different zip files. One is training, one is Orchid. And this one, if you download this file from the competition, like the official website, it will be with a bunch of image with a file called label.csv. But here I already pre-processing it to the format as we have the directory have the train and the eval directory. So I already separate the data to two different folders. So to help us, which because we here, if we want to use the functions that under dataset, which is dataset.image folder, we need to change. We will design our folders into like this one, and we have the two folder, meaning we have the training set folder and then the evaluation set folder. And for each folder in the training set, we have a folder like this one, 218, meaning that this is the label 218 object. So the image under this folder will also all consider as the label 218.
So how many species of the orchid we have?
For this competition, we have 219 different.
So each directory stands for a class.
Yeah, but like you can name the folder with the actual label. Also, you can name the folder with whatever you want. Then the image folder will help you to rename it to 0 to something. You have the index.
So when they download the data set, for example, training.zip, they can.
They have to do this by themselves. Like.
Okay, so this is how you separate the training data.
Yeah.
Oh.
I read the data and then also read the label CSV, and then create the folders by the labels, and then move the image to those corresponding labels folder.
So for other people, when they download the data set, they can have their own way to separate evaluation and training.
Yeah.
Okay.
So this is, you can also not using the image folder, but in this sample code I use image folder to easier to construct the data set and also put it into a data loader. So okay, so go through the picture here. So here I like for a training set that the official website provide. For each species, we only have 10 images. So here I separate as 7 to 3. So we have 10 pictures for each for the training set, and then 3 for the evaluation set for each species. And as you can see here, after 20 epoch, the accuracy for the evaluation set is almost 77%, and training is like almost 95%. So it's it still have like 24%, 23% for you to improve to get a good price or the ranking for these competitions. So here is the unzip, which is the one of the package that Linux have, and here Q means quiet. So if you did not use this parameters, this argument, then you will keep popping like the lines telling that this object already be extract. And here is a destination. So it will be the file here will be extract to the data under the data set. So which is here. So okay, so this is the transfer learning for computer vision tutorial. So this is a
question. So you are mentioning training.zip this directory, right?
no, this lib file.
Okay, this is not. But you have another directory, Orchid.
Oh, this
Will
is.
you explain that directory later?
So yeah, okay. So this orchid.zip is another data set I found on the internet. So if you wanna extract this, you just change the file name here to the from training to orchid. Then the data set will be like here, like this one. And this for this example, they have 51 species.
So why do you find another Orchid data set by yourself?
Because the first巡迴課程, how to say, the first tutorial is like March 28th, and the data set that the official website release is on April 1st. So at that time I don't have the data set yet, so I found another auxiliary data set on the internet.
Yeah, so I guess we really need the training data set instead of the OKID data set because the OKID data is actually found by yourself, right? And there's only 51 species. Okay. Yeah, however, for the competition, there are 218 species, so I guess we have to apply the first one. Okay. So because maybe the labeling different, not the same. Yeah. So I guess we are not able to apply the two data sets to train our model in the same time.
Yeah, right. But like you can use the semi-supervising to train a model that classifying the flowers and then apply this on the orchid species.
Maybe you can train more classes to see if it helps you for the target.
Or it might be helpful. Okay. Even though maybe the labels are not the same.
Or even you
for
can
the
use.
first step, you can use just the data set that the context provided.
Yeah. Or even you can use few shot to learn because our data only have 10 pictures, so you can use few shots to do the classifications.
Yeah,
so
this is why I'm also very curious that why they only provide only 10 figures for each species. Yeah, it's still not enough at all. Yeah, so normally we have still have 100 figures for each class, which should be sufficient, or maybe as a limit, maybe the lower one to have the training data set. Yeah, so why they do not only provide only 10?
Because when we evaluate this data set first in our lab, the accuracy is very, very high.
Okay.
So they just suggest us to reduce the number of training set.
Okay.
So maybe people can more concentrate on the model development or model design that improve the accuracy.
Okay. Yeah, it will be much
Originally, we have a lot of images in the data set, but we just release just part of the data set.
So it is possible that we get more data set according to for this 218 species.
This species is very particular species from the industry. So people cannot find the same species from the website. But they are encouraged to use other species as external classes to help to improve the model.
And also we encourage like different technique to improve the model, like different ways to do the augmentation for the image. So instead of just doing the classification, we can focus on the different scale of the technique. Like you can either do a pre-processing, or you can do a model improvement or something else like that. So this is what they said for just providing 10 images. So this is the PyTorch tutorial I get from the official website of the PyTorch. I modify it. So it demonstrates like how to use the pre-trained models to fine-tune the text on the downstream text. So instead of just randomly initialize the weight of the model, you can just get the weight from the model that already trained by other company like Google's Facebook AI or else. So here, like the ResNet I use is trained from the ImageNet dataset, which includes 1.28 million images as the training set. So the transfer learning will divide to, not divide, like we have two different, we have two common situations that we refers to transfer learning. The first one is we use the data set and fine tune on the neural network that we take from the others, or like for this one, we will updating the weight in the models. The second one, like we use the transfer learning models as the feature extractor. So here the layers are freeze, so we won't change the weight in the model. Just treat this as a model extractor to extract the features from the images. So this is the model training. So the training mostly the same. Like we have the model, and then we have the data loader, and then we take the instance in the data loader, which is a batch, and then for each batch we enumerate it, and then for each input we have the label, and we use the input label to the CUDA, to a GPU, and then we use the GPU to compute the image and the labels difference by cross entropy, and then we use that loss to backwards to the neural network and update its weight. So here, in the Orchid competition, we use we input the image to the models, and then we have the corresponding labels, and then for the image that put into the input layers or further to the hidden layers. The hidden layers can be 0 or even greater than 0. Then we have, after the input layers, we have the output layers, and then we at output layers we will do softmax and then get the like the percentage for each label, each classification result. Then we use its loss, use cross entropy to compute the loss, then do a back propagation. So here is a code. Here we import the package that we need. Then here, this is wait. So this is the whole code for this sample code, and we will divide it into different parts to expand it. So at this stage, you can simply run the execute. Then you will start to compute. Wait. Oh shoot. Here we change our execution stage to the GPU. So we have GPU here. Then we run this cell, and you will start to compute the. Oh wait. Anyway, you will start to compute it here, and here we'll get the error because I didn't run the previous one because I terminated the stage already. But you can do it. You can just press it, and you'll have the result. So here is the what data set will be. So we have the original data set, and here I separate to, like we have 10 pictures for each species. Then I separate it to training set with 7 pictures, and here 3 pictures. And then here is like if you want to do the test set, you can separate by yourself. But here is a 10, and then I separate the training set and validation set, which is 7 to 3. Then the actual 7 pictures were involving in the machine learning algorithm to adjust the weight in a model. And the last 3 pictures will just do the evaluation for us, for the data scientists to evaluate how well the model perform on this data set. And also you can use the 10-fold or K-fold validations to have many times of validations, and then you average it to get the 主观客观的to get a average loss to see how well your model would be. So here is a preprocessing. So here we use the torch.transform to do the image processing. So here we use a resize, because the image that the data set have will be 480 to something, 480 to 640 or something. But for the ResNet, the input size should be 224 to 224 or 256 to 256. So here we use resize to resize the image to 256 times 256. And we use the horizontal flip, randomly horizontal flip. They have like 0.5% to 50% to flip the image horizontally. And here we use 2 tensor and then normalize by these numbers. And so why we have to normalize with this number is because for the ImageNet dataset, the scientists compute the image means and standard variance. And then after they adjust the pictures, the RGB by this value for the mean and variance, it will become the Gaussian distribution. And here we do the same as the evaluation set. But here we did not do the horizontal flip because the variation we don't have to make the variance of the pictures. We just simply do the evaluation here. So here you can see that the data transform, the variable here is a dictionary type. So when we print the data transform variable, we will get the dictionary that have trend and val as a key, and then compose a series of image transformation as its value. And here is what we load how we load the data. The torch.ut.data, the API already give us a function that like we can quickly build the training set and the validation set. So here we use the dataset.image folders. So which when you the parameter, the variable pass into the image folder, you just pass the path directory to this function, then you will treat the folder, the path under it, as the way to separate the data. Like here, if you have the dataset folder, then under you have train and val. Then this means training set and evaluation set. And then the folder under training and evaluations is a class, which is its label. Then the label, the folder means label. Then the image under this label refers to the image with corresponding labels. So like the bf1.jpg here, its label will be class 1, and the uf1.jpg here, its label will be class 2, and etc. So here our directory will be dataset. Here we change to training. Okay, whatever. Training or Orchid, both will be fine, because we won't execute it here. We will execute the code already on the top, on the cell above.
The second dataset you have, right?
Yeah, this is a second dataset that I download from the official website. Then here we have the instance. It's called image dataset, which is also a dictionary that we here have x, and x will be the value from like in the list. So we have trend and value eval here. So when we print this one, printer image underscore dataset will have two keys. One is trend and one is eval. So you will have the description like this is the dataset image folder, and the data point, which is the data involved in this image folder dataset, will have 2403 image, and the root location will be this, and then is the information here. Because here we also put the image dataset and image, which is this one. Okay, image dataset, this one, and also the way to transform it. I remember. Oh, here. Oh, image dataset already put the path and also the way to transform the data in here. And then after we have the instance of image dataset, we put it into the data loader, which is the torch.utilities.data loader from this one. So this is like a bracket with the bracket. So here we have the instance here put into the data loader, and we have a batch size, which you can change it to 8, 2, or even smaller numbers if your GPU is smaller. Like when the batch size greater means you can run faster because you have lesser batch to evaluate, to train. But like how's it? Batch size getting greater means you have more variance, more uncertainties to the images. So you can change the batch size to smaller to get better result. But it is not ensure that it is not a good way to say when your batch size decrease, your model will increase, or your batch size increase, your model will increase. It depends on this dataset. So here, training you can set to true or even false. It doesn't matter. And here, these two variables is not necessary. But if you in here, I do the visualizations. I have to know its labels and its label names, and also its dataset size to decide how many grid I have to put in here. And device here is like I assign the values to the GPU 0. So here is CUDA 0. If you want to assign it to CUDA 1, then you can use CUDA 1, GPU 1 and CUDA 1, or you can use OS.environment and the CUDA visible device to decide what GPU will be used in the script. So here is the visualizations. So we do a transpose because wait. Okay, we do a transpose because we want to transfer it to the NumPy array. Because this one is the PIL format, and we transfer it to a NumPy format. Then also put it do it with the means and standard variance. And because the normalization is like we do the operation like subtracting with the mean and then divide the standard variance. So here we multiply back and then add the mean back to each channel. Then after the series of operations, you will get that this one is the image with the normalizations, and this one is the image without the normalizations. So this is the model training. So model training, because we cannot ensure that the last epoch will be the best result for the model. Like your model can even like overfitting and then start to decrease its accuracy for the evaluation set. So here we use a variable to store the best model. And here we use deep copy instead of shallow copy. So the model here, the variable here will be independent to the model that trained in the script. So here we have we initialize the best SEC as 0 to 0. So 0.0. So when the accuracy increase, the number will be refreshed in the loop. So so in each epoch we have like we can do 20 epoch, 30 epoch, or 100 epoch. It depends on you. Means how many times the whole data will be repeat. So if you have 100 epoch, then the whole data will be run 100 times. And here we have the data loader. The phase means training phase or evaluation phase, or you can even dividing the functions to the training phase function and evaluation functions. But here I combine it together. So here we have to put the labels, the input, which is our image, and then labels, which is our labels corresponding by the folder name. Then we put it into device, and we do so for the training phase, we set its grade, the required grade as true, so the optimizer can update its parameters. And for the evaluation phase, we set the gradient as false, the required grade as false, so they won't compute the gradient, so the speed will be faster since the GPU did not require to compute it. So here is the model will be the model here. Here the model here I set I declare is ResNet 50 or it's 18, or you can use 50 or 152 or something else, or VGG. Just change the less output fully connected layer to the corresponding the dimension for it. So here we put the data into the models and we get the output, and we take torch max, which is the XSX will be 1, which is like we take the maximum numbers for each row for each row. So which means that so our data will be n to the 219. So for each row we have one greatest number, which is the predicted labels for this instance, for this input. And then we put the value here to the we put the value here to the output here to the criterions, and then we get the which is the cross entropy, and then we get the loss. And then we use the here we set optimize the 0 grade to clear the gradients that's stored in the neurons from previous instance, and then we use the loss.backward to get the gradient, and then we use to get the loss, and then we use the optimize.step to compute the gradient again. So for each step we get a computer gradient, and then we clear the gradient again, and then get the gradient by computing a loss. And here we just this is for statistics, so we will summing the loss and then correct labels, and then to calculate the each epoch loss and then the epoch accuracy. So here is another option. You can add the scheduler to change the optimizer. Like the optimizer might be 0.005. The learning rate will be 1 to the negative 0.06 to become 1 to a negative 0.5 by the scheduler. So the optimizer will keep changing if you apply scheduler to the optimizer. And here is the epoch loss. So here if the condition holds, so if the condition that we have the better epoch accuracy, then we will store this model by using deep copy. So you can just save this model instead of saving the less epoch model, because the less epoch model might not be the best for the for your model performance. And here is the visualizations that done at here. So here we just use matplot to come to draw the lines, and then also use matplot to do eval loss. I didn't store it. Also here we have the training loss figures, and we have another eval loss figure, but I didn't run it, so it becomes like this. So okay, so here is a way you can. Here is a part you can try. You can change the resident 18 to 50, or change to VGG 16, or change to DenseNet 161 or else, or even you can change it to your self-defined CNN models, and then the last remain the same. Then you can put your data into the model and run this code, and you will get a corresponding result for it. So here is, if you use the data summary or use print model, here you can see the operations that the model do for each. So for each layers, like here we have conversion 1, and then batch normalization, and rate rule, and then next pull, and etc. Like this. When we have 5 layers, 4 layers for the repeating sequential block, and we have the last layer that fully connected to get the maximum label probability to output as the possible labels for it. And that's the whole code, simple code. Does anyone have questions for running this code?
So I think after we have fine-tuned the model, and we actually didn't retrain the model at all.
We fine-tune on the model.
Yeah, maybe in the end of your code, and we have to make some fine-tune, right?
Here, just run this line.
Yes.
With so start runtime. Oh, okay. Just wait, give me a second. So I run this code again. So does anyone have questions with running this Colab notebook?
You have to maybe put the training data set into your Colab directory.
So the Colab notebook and the training dataset should be in the same same folder or same directory.
Do you provide the dataset to students after split the dataset to training?
Yeah, all open.
Okay.
And then should we maybe to upload the train model or maybe the code we wrote?
Oh yeah. So for the submission template, which they didn't provide it yet, but the data should be in this format. So this here, the first column will be the image name, the file name, and then second column will be the corresponding labels for it. For example, the image A output is, your model output is the label 1, class 1. Then here will be the 1, and here will be the A.
So the label index starting from 0 or 1?
Label image will be the random number.
Random number?
Yeah, it's like the label will be 0 to 18, but the image name will be random number. This one. Like the name will be just generated from A to Z and then 0 to 9. Just the composition of the 36 numbers. 636 number, yeah. So here you can see the code is running, and here they download the ResNet from the PyTorch hub. and then save into the root directory. And then when the strict code, it will access these models and then load to the memory, and then start running. And here we put the model to the GPU, and then put our data in the GPU for faster computations. So here for the first epoch, I haven't done yet, but here you can see that the data flow will be at here.
So anyone have any problem to relate to the notebook? Right, so I think there should be no problem for everyone to run the Colab notebook.
Okay.
Maybe it would be a very good midterm topic for everyone. Yeah, because I have asked them maybe 2 or 3 students in a group. Yeah, so maybe they could maybe just try the data set as the midterm presentation.
Do you have a discussion board on the website that they can like raise their questions?
So here we have the discussion board at here. Here, click the discussion, but mainly in Chinese. So the foreign student may have to, like, as a student that who understands Chinese, to transfer this. And here is one of the questions that the participant complained that for each label only have 10 samples, which is really insufficient for doing the classifications. But here we have another participant saying that if you can even do the semi-supervising, like you scroll the picture on the web that relating to the flowers, and then use the fine-tuning, like semi-supervising and fine-tuning way to further train those flower models to fit your ORCID dataset.
Okay, so if you have any questions, you can post on the discussion board. Liang, I will try to reply your questions and how to solve your problem.
And wait, did not. The dataset, total dataset. 他们改了。Oh, here, and here you can download the dataset. Here, till now only release training.zip, and at May 30 will provide. If you want to join the competitions, on May 30 they will provide a public dataset and then private dataset. Then we will have the public leaderboard and private leaderboard for the competitions. 老师，这个是线上的比赛吗？还是要去现场？线上的。
什么意思？
这比赛要去现场，还是只要线上 leaderboard 就好？
线上就好。
Okay. So the competition will be held online, so you don't have to move to the like other place to join the competitions. Yeah. So it's pretty flexible to decide whether you want to join or not. Yeah. So it will be like this. I think they have English version here. So the English version might not be pretty fancy compared to the Chinese version, but here is the English version if you're interested to these competitions.